Hello guys and welcome to another video with Cass on the Maizuma channel. Today we're going to take a look at the control signal amplifier. So I have four solutions that I think could be interesting discussing, so let's get started. So the puzzle consists of this. So we have control in, which is a simple input, and control out, which is a simple output. The signal from control in should be multiplied by 2 and copied to control out. Okay, so basically they want us to do something here in between so that whatever comes in from this side gets multiplied by 2 and sent to this other side. And this is a standard solution. So basically we copy the input to the accumulator because accumulator can do math. And here I just add the value of the accumulator on top of itself. And the reason why I did this is because in real life, some architectures are a little bit slower if you use the multiplication instruction. So it's equivalent to multiplying by 2. I'm just adding the same value on top of itself. But I did this because I wasn't trying to save on power or something like this, but I just found out that it doesn't matter for the game. And finally we output this. So yeah, pretty standard solution. This is how the waveforms look like. Just trying to run the solution. It's a very simple solution. Okay, so yeah, this is the final result. So let's get back to this main menu. So this costs, the total cost is 3. So actually all of my solutions have the same cost, but this requires 240 power and uses only 4 lines of code. Alright, so the idea with this one is to try to save on power by just doing things when changes happen. This kind of makes sense, right? Alright, so in order to save power, you need your system to be doing nothing most of the time. You need your system to be sleeping most of the time. So what I did here is something that detects changes, and when something changes, it does something about it. If it doesn't change, it doesn't do anything. And this is done in order to take advantage of this this input. See here, we have those long strings of no change. So hopefully these things would compensate for everything. So let me walk you through some of the waveforms. So if we step in, let's see if we can get. So yeah, the input is now 50. So it will copy, it will multiply by 2, then it will fix the accumulator so that the accumulator will always match the input. So you see here, yeah, if I execute one more instruction, the input is the same as the accumulator, and then the output is twice the value. So we sleep, and now if we keep the same value here, so if we get 50, P0 is going to be equal to the accumulator, and none of this is going to be executed. So yeah, this is not going to happen now because the input is going to change. So it's 95 now. So let's advance a little bit. Let's actually advance to this point in here. Alright, so now the accumulator is 0 and the input is also 0. So you see here, none of this code gets executed, so we are saving on power on these cases. And it's not just when it's 0, but well, in any case like this, for instance, here we have the input at 25 for 3 ticks, 3 consecutive ticks. And this works like this. Yeah, so the idea is pretty cool, the algorithm's really interesting, but the input data, it changes too much, so the algorithm gets executed all the time. So the method that we use to calculate the changes gets executed all the time, and we suffer from this because we end up executing more instructions than we are supposed to. So yeah, just showing you guys an interesting idea. But look at this, this is what I'm calling the zero exploit. We are always trying to compare it to the basic solution. It uses less power, all right, and only 6 lines of code. Again, let's try to see what this is about. So if you check out the verification tab, you will notice that a lot of the times those long strings are just zeros. So I decided to make 0 a special case. All right, so if something is 0, we do no calculations, we just move 0 to P1. And if it's not 0, then we do the calculation, the simple calculation, so just copy, multiply by 2, and send it to the output, and sleep. So yeah, let's see what this does. So yeah, This is the difference now. Can we pause the simulation and maybe run something interesting in here? Possibly this one. Yeah, if we step in, see, we are only executing three instructions in here, which is interesting. So yeah, so this works. So if we take into account only the zero, it works. So I'm calling this the zero exploit. So we can use less energy if we do that. And finally, I came up with the data exploit solution, which uses even less power. So what I'm about to show you is what I call a cheaty solution. And there's a lot of this in this game. So as you saw, every time we beat a puzzle, we see this this output in here. We see what others, how good other players did in relation to our solution. And when you see something really off the charts, it's usually because someone is cheating, which is what I'm going to show or even or maybe teach you now. So what I did here is to break down the data into three different cases, because I noticed that this graph, although the input is analog, it doesn't range all the way from 0 to 100. It can't have just any value. It will only be either 0 or 25 or 50. So there are only three outputs that we need to take into account. So it's either going to be 0, 50, and 100. And the advantage of this is we don't do any calculations. The values are all pre-calculated as well. So we start by moving 50 to the output, and then we use this instruction TCP. If you don't know what this instruction does, you need to check the second part of microcontrollers, which is one of the tutorials on my channel. And yeah, so if the input is less than 25, then we output a 0. Once again, no calculations done. And if it's not, then we output a 100. And that's it. No calculations. We just have two cases. We are executing a very small amount of instructions most of the time. So 1, 2, 3 instructions. Yeah, we're just executing 3 instructions and sleeping, of course, all the time. So yeah, very simple solution in here. But I consider this cheaty because this solution is modeled specifically after the verification input that we have in here. If they change the verification code somehow, or if they make the system respond to the full range of the analog signals that can come from the control in thing, this solution would fail. And this solution, like the basic solution, would never fail because it actually does the calculations. So yeah, it goes for a show to you guys what some of the things that you can do. So data exploit solutions are very common in this game. This is how people get their best solutions usually, and I don't like to take this approach, and usually we will try to avoid that. We'll try to avoid modeling our solution according to the data that's going to analyze, if possible. Okay guys, I can't wait to show you guys the solutions to my next puzzles. Thank you very much for watching this one, and see you next time.